Welcome back, everybody, to what is your final Regents lesson. You made it? Well, almost. You still got to make through it. Then you got to do the homework. Then you're done Regents, except for the final. But it's neither here nor there. This is the last one. You're done. You made it. Yay! So last thing we were talking about was radiation, all the kind of crazy things that happen to it with it, how it happens nuclear. I think the last thing we talked about was like nuclear energy, right? First we started out like what is radiation, the different kinds like alpha, beta, gamma, and zero mass plus one charge, minus one charge, mass of four, charge of two, that kind of thing. And how well they went through stuff. Like alpha radiation doesn't get through anything. Beta gamma radiation gets through some stuff, but maybe a lead vest is all I need. And the gamma radiation, maybe you're not gonna stop gamma unless you have like a gamma absorber. But really, it can go through just about anything. And then what did we talk about? Oh yeah, nuclear equations, right? Like what happens when it decays, like what does it look like? Remember, we have artificial and natural transmutation. Natural transmutation is where you have like your reactant, and there's the arrow, and then there's your products, right? There's one thing that naturally turns into something else, right? So it's just like it just does it on its own. Whereas artificial, it's the same thing, only opposite, where it changes into something completely different. Remember, transmutation, it transforms and it mutates. But we have to add something to it. So for that equation, there'll be like two things, right? There'll be like some kind of element plus usually it's like either alpha radiation or neutron, because that's easy for us to get and sort of zap it. And those things kind of come together, or maybe it's breaks something and makes a new element, transforms and mutates. And then we went to fission and fusion. Fission is where we like break a nucleus in half. That's nuclear power, and that's what our nuclear bombs are. Although we've gotten creative and we have like a sort of a combination fission fusion bomb, which is a hydrogen bomb. Man, like mind-blowing amounts of energy out at once. Anyway, let's go to nuclear power, where you can like slow it down, make it really dilute. And there were 3 videos that were previously unavailable for Mariah watchers, but now I just unlocked them, so you guys can go check those out. They're actually really worth watching. They're pretty cool. Deal. Best video I've ever seen about thorium. Get out there and look up thorium, because thorium reactors pretty good if you ask me. I mean, that's like how could kind of hard to go wrong, right? Never gonna find a perfect solution, but thorium seems pretty darn close if you ask me personally. But anyway, that's not for nothing. Last thing we're going to talk about is this. Wait. And that. Wait. There. That. Wait. No, that right there. I can't do that pointing thing. I'm never going to be able to. It's the last one, so I'm not going to. Anyway, uses of radioisotopes. Now, let's just remember really quick. Like, what is a radioisotope? It is a radioactive isotope. We're not trying to get crazy here, creative. It's a radioactive isotope, and we can use these things in all kinds of ways. In medical treatments, like we've all heard about, like there's even like if you go to the hospital, there's like a whole section called like nuclear medicine, right? Here are some of the most common ones. Iodine-131. This is a radioisotope. Is most often used for to analyze thyroid problems. So thyroid is a gland that lives like right behind my bow tie here, right? And that regulates, it's basically a little gland that makes lots and lots of hormones. And those hormones regulate like everything. Like most people hear hormones and they think like, puberty and, blah, blah, blah. But hormones are how our body talks to each other. There's like bajillions of different kinds of hormones. Only a very few are related to like puberty and whatnot. So thyroids, getting back to it, this creates hormones for our body to communicate to itself, and it regulates all kinds of metabolic processes. And everybody knows someone with a thyroid problem. If you don't know someone with a thyroid problem, they just haven't told you about it yet. And so what we can do with iodine-131 is we give somebody iodine-131. And the reason we do that is because the thyroid absorbs iodine really, really quickly, really, really easily. And iodine-131 is radioactive. You dig? So we give it to someone, and like you can either just usually inject it in the veins because it's pretty quick delivery that way. And if the thyroid is working normally, it'll absorb iodine at a normal rate. It's basically take a picture, compare compare the picture of the person with what it's supposed to be. And if the thyroid glows with the proper amount of radiation, then your thyroids are working well. However, if it's glowing a little extra too much, and they can measure how extra too much because it's radiation, basically a fancy Geiger counter, and they can measure it, then we can say they have hyperthyroidism. In other words, the thyroid is working way too hard, and that means it's pumping out too many of the hormones, which will cause irregularities because of too much hormones. And then the same thing, only opposite, if there's not enough radiation in the thyroid, not as much as expected, that means that's hypothyroidism. No, is it hypothyroidism? Like too low, it's like not working fast enough, so there's not enough hormones, which causes imbalances and problems in the other direction. So there's iodine 131. Super duper convenient little stuff right there. What's our other thing? Oh yeah, TC99, technetium 99. Now this stuff has a pretty long half-life for medicine. Like I think it's over 2 years, which is bad. Like most radiation that they use in medicine, you only want a half-life of a few days, maybe a couple of weeks. Because think about it, you don't want that stuff sticking around in your body for that long. However, with things like this, with technetium 99, one of the things that we can do is we can attach it to something that is flushed out by the body pretty easy. So while it has a very long half-life, it doesn't necessarily stay in our body. And so I want to look over at this dude over here. This man right here, this is a picture of a technetium 99 analysis. And so one of the things that happens with cancer is this thing called metastasis, where like a cancer, so if you think about it, our body is made out of organs, right? Let's look at our liver. Our liver is this big gooey blob. It's like kind of like brownish reddish color. Now, the reason the liver stays together as a liver is because all the liver cells have these little molecules that link them together, right? That stick them together, so the liver the liver cells all stick together and form a liver, right? Problem is with cancer cells, it is a problem. They lack a lot of those connecting molecules to hold the cells together, and so they're very what we call friable, or they can break apart really, really easy, and that's called metastasis. When a clump of cancer starts shedding cancer cells, and that's when the cancer goes throughout the whole body, and that is dangerous. That's when it gets bad. That's really what kills people. If the cancer stays together and contained inside a membrane, which sometimes happens, we call that a benign tumor. We go in, cut it out. It's all in one ball. We're perfectly safe and fine. We go home the next day. This man, however, actually that guy over there, he had prostate cancer, and I'm not sure if this is it. Again, I'm not a medical professional, but I think this is the prostate right here, which is where the original cancer happened. Now, many prostate cancers, while not great, they grow very, very slowly. So it's not like the prostate cancer itself is going to kill you, because this is also an elderly individual, so he's not going to live another 50 years for this prostate cancer to get him. But what is a problem is if that cancer metastasizes and spreads throughout the body. So what they do, in order to decide how to treat, they will inject technetium 99 into the body, and then they take an x-ray. And this technetium 99 is usually connected to a tag or something else so that it can be washed out of the body. And if we come over here and look at this individual scan, this lump right here, this really, really dark spot, that's the bladder. So that's sort of where it's collecting because it's been in the system for a while. And we have these really great things called kidneys that get rid of all the poisons and toxins from our blood and put it into our pee-pee. So we pee it out and get rid of all of the toxins that way. That's why they make you pee in a cup for a drug test. A drug is a toxin and a poison. Kidneys take it out, put it in the bladder to get rid of it. So let's check it out. So what we do is we inject technetium 99 into our patients, and then we do basically an x-ray. And as you can see right here, and that's about where our kidneys are, and you can kind of see it trickling down. This could be a kidney. It could be, what is that? An adrenal gland, but this tube right here tells me that that's probably just a man's kidneys. Not much of a problem. this isn't much of a problem. That is sort of like expected, that teeny little dot there. However, let's go through this and look. A very dark spot right here indicates there's some cancer there. Also here, also here, also here, a little bit here, as confirmed on the other side. They're in the same spinal cord. Right, these two are connected. Those are verified. These are verified. So this one is probably on the front. This one is, I'm sorry, no, the top one is probably on the front. See that one on the bottom there? It's probably on the back of his spinal cord. You can see his femurs, fibula, tibia, all throughout. This leg is sort of in trouble. And you can see, because technetium is very radioactive, it can be absorbed by cancers. You can see that this individual, while the prostate cancer itself hasn't caused much, it has metastasized, and this individual probably will be undergoing what we call palliative care. In other words, make him feel comfortable as he goes out. Kind of depressing, but it's like part of life is like the end of life, and things like this help us make good choices, right? So the man can decide what he wants to do. Does he want to fight it and go through like gobs and gobs of chemotherapy and lose his hair and puke for 3 weeks for another month of life, or does he want to just, you know, go home, sit in his easy chair, and hang out with his grandkids for his last few bits of time? It's all about choices. So that's what technetium-99 is used for. The next one, cobalt-60. This is actually a really common radioactive substance. It is used for killing tumors. So one of the things we would do with cobalt, because it spits out gamma radiation, which is like really high energy radiation. Cobalt-60 spits out what we call ionizing radiation. That's the bad stuff. It will burn you. There's no amount of this that you want to get. It's bad. Unless you have cancer. So what we do with the cobalt-60 is we attach it to a molecule that has been engineered by science to grip onto a cancer tumor, and there are also some molecules that are absorbed by the cancer cells, and so it goes inside the cancer cell, and then the cobalt-60 transmutates, spits out some radiation, and we hope that it smashes into that cell in a way that kills the cell. And what we do with radiation and chemo is we fill the body with as much radiation as that person can handle. It's like an art and a science together, where we want to like basically make it so much radiation that the cancer dies, because it's just little teeny cells, but the person who is huge can recuperate and recover and survive. You dig what I'm saying? So when people get chemo, it's often months, sometimes even years before they fully recover. But that's how that works. Cobalt-60 spits out radiation, ionizing radiation, that can be used to kill tumors. And if we're smart and good about it, we attach it to a tag that gets absorbed into the cells of, into the cancer cells, and bam. Cobalt-60 is also used to irradiate food, which means to kill like germs and stuff. And let me see if I got, oh, there it is. This is what we call an irradiation plant. I don't know how big you can see it on your screen, but here's basically how it works. Y'all know what like Ebola is, right? Or well, no, what is it that they get? The food contamination? E. coli, yeah. Dude, food poisoning is like not good under any circumstances. A lot of times there's food poisoning and like everyone's like, oh, you're fine, just a little bit of liver damage. Like, but no, man, there are people who have like permanent liver damage. There are children who are killed. There are old people who are killed. Food poisoning can be horrible. And also the way that our food chain works now, it's not like one person is going to get food poisoning from one little farm. It's like there's a giant factory farm that makes like 75% of the baby spinach for the entire country. So when that gets contaminated, it's like tens of thousands of people are poisoned. So to make it clean, here's what we do. Basically, we get all of our food and we pack it into these little square things. It's like a big square container. I mean, it gets hooked onto this conveyor belt. The conveyor belt goes into this thing called an irradiation room. I don't know if you can see, but it's covered with like giant thick layers of concrete. So like hopefully to like insulate it. And also not just concrete, but they use special material that absorbs gamma radiation extra good. And it goes zinging back and forth through this conveyor belt. And underground are stored cobalt-60 source. And it's in water, because water can absorb all the radiation fun times. And then when it's time to irradiate food, they take this thing and they lift it up out of the water, and these little where's my little pen thing here? These little square boxes or like canister things here, these guys are just passed right like on the conveyor belt, gets put really close by the radiation. The radiation zaps all the food, and then it comes out this other side, it gets loaded up and taken over to your local grocery store. So the thing is, the radiation only really hurts living tissue, and if it's just baby spinach, man, it's dead, right? It's food, so it's not like it's going to give you, like, radiation isn't sticky, it doesn't stay there, it goes right through. It goes through and kills all the dead spinach DNA, but it also kills the DNA of any like E. coli or other bacteria that might be sitting on top of the spinach, so we don't eat it and get sick and like die and have horrible lifelong like organ scars and stuff. So yeah, irradiating food works amazingly well. Problem is people don't want cobalt radiation in their backyard because, you know, cancer. Not awesome. Also, the other use we have is carbon-14. This is how we know how old organic stuff is. And I mean like really old. Is it exact? Nah, it's kind of fuzzy because, you know, nothing is perfect. So here's the deal. Up in our atmosphere, we have our atmosphere is mostly nitrogen, right? And what happens is there is cosmic radiation that comes in from the outside. It hits an atom, and the atom goes and has a thing, and then there's a neutron that goes flying out, and that neutron has to hit a nitrogen-14, which then gets converted into a carbon-14. And if it's in the atmosphere and it's a carbon, it's probably carbon dioxide. Now listen to what I had to say there. First, we had to have the right kind of ionizing radiation come in from outer space. It had to interact with an atom in such a way to release a neutron. I mean, which happens. I mean, we have ozone and stuff there, so it can happen. And that neutron has to fly through our atmosphere until it hits a nitrogen-14 nucleus. I mean, these are not big targets. So, and then it has to form a carbon-14. So it's not exactly like this happens a lot, but it does, and it happens at a very steady rate. Because we're in outer space, we're getting washed by radiation by the sun, which burns at a pretty steady rate. So the amount of carbon-14 in our atmosphere is pretty gosh darn steady. Pretty gosh darn. And fun fact, it does fluctuate, and we can go up to Antarctica and the North Pole, and we can dig ice cores, or cores, like ice cores, you know, like a big tube, it's like about that big around, huge long, and we can date or see how much carbon-14 was in the atmosphere because ice has little bubbles, and we know how much ice is made each year and blah, 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 stuff like that. So, anyway, here's how it works. Me, you, the Iceman that was found in that glacier, and like any living thing, we are part of the carbon cycle, right? So there's carbon-14 floating around in the atmosphere created by like cosmic radiation. That carbon atom, because it's carbon in the atmosphere, it's carbon dioxide. It gets absorbed by a tree. Let's go with an apple tree. So the apple tree absorbs that carbon dioxide into its leaf. It does metabolic stuff, and then it makes an apple. And some of that carbon-14 is in the apple, right? Because that's how it works. Plants absorb carbon dioxide to build their structures. Then you and me, we grab that apple and we eat it, and that apple is used by our body to build ourselves. I mean, we are constantly changing things over even after we're done growing. Like every 10 years, our skeleton has washed itself out and replaced itself. Our cells are constantly being replaced. I mean, look at our skin and our hair. It's constantly growing and changing, right? And getting changed over. You guys know about like mitosis and stuff. I'm sure Craig's taught you all about that good stuff. So anyway, we are in what we call the carbon-14 cycle, and we reach a state of equilibrium with the amount of carbon-14 coming in, right? And the amount of carbon-14 going out as we like, die and decompose and waste and stuff as our body metabolizes. And we're all at a steady state. So the amount of carbon-14 in the atmosphere is sort of like this kind of is relative to the amount of carbon-14 in the plants, and us, and everything. So all living things have sort of the same amount of carbon-14 in them. All of a sudden, I hope we get old, we die, right? Like maybe in a cave somewhere. If we die, we don't eat any more carbon-14. Our bodies aren't being built anymore, so we're not adding any more carbon-14 in us. We are out of the carbon cycle. And what happens is all the carbon-14 in us starts to like transmutate. But the problem is there's no new carbon-14 coming in, so the amount of carbon-14 that's in the atmosphere is like up here, and then once we're dead, it slowly transmutates until it's all gone. But it takes like tens of thousands, like a very long time until all the carbon-14 is gone. By the time all the carbon-14 is gone, like most of the organic material is probably gone anyway, and we're looking at a fossil. You guys get what I'm saying? So the carbon-14 is used. I mean, that's how we can tell. And it's not perfect. It has a range of like 10,000 years. But, dude, when you're talking like 60,000 years ago, plus or minus a few thousand years, it's not that bad. It's the best that we got. Also, I kind of mentioned it sort of, but this one, uranium-238, we use that to date geologic formations, like the Adirondack Mountains. Like the way that we know that they're old isn't because we're like, oh, I think so. I have a hunch. I think. Like nobody in science goes with hunches or like, well, it's probably because that just makes sense. Nature's not here to make sense for you. So all these people who are like, well, it doesn't make any sense. Well, they need to just shut up and they need to science. Because what we do is we use uranium-238. And so if you go up into the Adirondacks and dig a core of granite, which is what the Adirondacks are, you compare the amount of uranium-238 to the amount of lead that's in the rock. And the older stuff is, like uranium-238 is radioactive, and it basically decomposes into lead. So that ratio of uranium-238 to lead kind of gets lower and lower and lower. Like the amount of uranium gets lower and lower and lower and lower and lower over like geological amounts of time. But, you know, that's a lot of time, way more time than humans. So, of course, it's not going to make sense to humans. We only live for like maybe 100 years in the mountains, way more than that. So that's how we date geologic formations, is with uranium-238. Because remember, I said way back up in the beginning that this rate of like transmutation, the rate is as steady as the universe. Nothing changes the rate of decay at all. So we just kind of work backwards with our half-life stuff that we did before, and we can kind of figure out how much we started with. You dig what I'm saying? Like if we look at the ratio and like, wow, this is only 1/8 of what it ought to be. You just kind of work backwards and figure out how many half-lives there were, right? And we already know what the half-lives are, so bam, science. All right, now this last one, or second last one, are tracers. So we sort of saw tracers up here with this guy, right? We put something radioactive into a living thing or in the environment, and we just followed it with like an X-ray camera, basically, like something that takes a picture of radiation. So with tracers, we can trace fertilizers and watch it being taken up into crops. We can also phosphorus is a major source of nutrients in fertilizers. Phosphorus 31 is radioactive. Not a terrible long half-life, so it's okay to put it out into the environment because it doesn't last very long. What we can do is farmers pay gobs of money putting fertilizer on their soil. Problem is, a lot of that fertilizer gets washed right off the instant it rains. Problem for the farmer because their money is being washed out of their field. Problem for everybody else because that fertilizer goes into the creeks. The creeks have too much nutrients. It chokes out all the native habitat or little squishy biological things. The creeks feed into the lake. The lake has way too many nutrients. It gets warm outside, and then we have blue-green algae, and it kills all the fish and kills all the dogs that go swimming in the water, and it kills people. It doesn't kill us, but it makes us really unbelievably sick. It could kill us, but we're not dumb enough to swim when there's an algae bloom. So what we've done is we've taken phosphorus 31. We go to a farmer like, here, take this bag of fertilizer. We tell them all about it. They put it on their field, and with the satellite, we just take a picture. And we can watch the phosphorus 31 drain. And we can say, hey, farmer, try plowing instead of like, if the hill goes like this, you don't want your rows to go up and down. You want them to go sideways. And sure enough, we did that, and the amount of phosphorus in our waterways dropped dramatically. Good for the environment and anybody who wants to go fishing. Good for the farmers who want to save money, and good for people who want to eat food made by a farmer. You dig? That's what I mean by tracing. We can like watch it happen. We also use phosphorus 31 to watch DNA transfer from a virus into a cell. So we can grow a virus inside a petri dish with phosphorus 31 so that the virus DNA is radioactive, and we can just watch it with a camera. We just watch it go from like one place to the other. It's so trippy. Yeah. Okay, where were we? Carbon-14. Take a plant, put it in a box full of carbon-14, and you can watch where the carbon-14 goes. You can see like where it's putting the carbon-14 and whatnot. We've even used this as in one experiment. There was like a person, a professor, who couldn't quite understand, like, it seemed like trees were communicating to each other, right? Like one tree got invaded by caterpillars, and then the tree next to it somehow like was able to like increase the amount of toxin that it produces in its leaves. It was something crazy like that. And so she was like, this is so weird. So she took one of them, like the one that wasn't invaded by caterpillars, and like encapsulated it in a bubble, and put like carbon-14 in it, right? And so they were watching how it like metabolized and everything. And like she had these out in the forest, like all separated. It was wild. And then they realized that trees are able to communicate to each other through mycelium in the soil. So there are actual chemical, somehow, we don't really know exactly what, but trees are talking to each other through mycelium in the soil. And how do we know that? Because we can expose one tree to carbon-14, and that carbon-14 shows up in another tree like 100 yards away. See, that one I don't know, but that's kind of what we mean by tracers. We can follow stuff along. You dig? All right, next one is industrial. Man, we can measure the thickness of materials. Big deal until you go flying in a plane. Right? Like, that fuselage needs to be made perfectly. And you can't, like, cut it in half to measure it, because then, you don't have a plane anymore. However, in the very, very beginning with alpha, beta, gamma, and positron radiation, we're talking about penetrability or penetrating power, right? So what we know is that, like, 1 millimeter of, beta radiation should be able to absorb, like 1 millimeter of metal should absorb this much radiation. And so we can measure the amount of radiation that can pass through a substance to determine how thick it is. You dig what I'm saying? Which is awesome. You scan the fuselage of a plane, and what you're looking for are like, make sure that everything is like this. Make sure you don't have like a little bloop, little bubble, or like a weak spot. You know what I'm saying? That way, when you go to like 35,000 feet, you don't, suddenly depressurized. Last one, gamma radiation used to sterilize food from cobalt-60. We talked about that. Let's wrap it up. Last bit for the year, risks, man. And if you don't know the risks of radiation yet, I'm not sure I can help you. This is what we call pulse knowledge. You guys get what I'm saying? Radiation can damage healthy tissue, right? It can give you radiation poisoning. It literally breaks down your tissue molecule by molecule, just like fire. It causes cancer, it causes illness, it causes death, right? It causes cancer when that damage hits our DNA and causes a mutation. It causes illness when we get so much radiation all at once, it kills so many cells that we experience like organ failure, and when we experience organ failure, we experience death. Or, cancer can also cause that. It causes genetic mutations that are passed on to offspring. This one is disgusting. This actually happens, I can't, Croatia or Bosnia or something like that. There is a kind of bomb that they exploded in the air, and I can't remember the exact size, but it was a radiation bomb. Wow, this huge explosion. Everyone's like, oh no. Okay. Everyone thought they were fine, but what it did is it exposed the entire population to a radiation that is known to cause genetic mutations to offspring. So this entire population of people started having massive birth defects. And this is forever. Like, that DNA change cannot be undone. So this is like a weird, modern, crazy, like science fiction version of genocide, where they tried to wipe out an entire population of people by destroying their DNA. And also, radioactive waste is difficult to store or dispose. Yes, nuclear waste from like a nuclear power plant is not as radioactive as the fuel, but the fuel is strong enough to light you on fire. This stuff is no joke. It will poison your water system. It will poison your food. It will poison your environment, and nobody wants it in their backyard. Not because it's not stored properly, but because if anything were to leak or get out, or even the slightest thing were to go wrong, you and your children are all going to have cancer. And nobody wants that. And also, it's so radioactive for so long that scientists are trying to figure out a way with symbols to indicate after our civilization is dead, the next civilization that goes digging in there in that mine for whatever knows that it's dangerous and stay away. Like, don't crack open this big cement vault or whatever. You guys get what I'm saying? Boom! End. Not end of lesson. End of year. Guys, you made it. All you need to do is uses of radiation for homework. And the reading part explains everything. Like every radioisotope you'll need to know is also listed in that reading. Do that. Upload it. Last homework lesson. Here's the situation, my friends. We have a final exam coming up. It's going to be, I think, we're going to do a Castle Learning thing. So it's going to open up. I'm going to give you, we have 9 till noon is the block that we have, but we're not spending the whole time. At most, it should take you an hour and a half. So what I'm going to do, I'm going to make it on Castle Learning. People who get extended time, don't worry, I'll make it double time for you if you want. But it really should not take more than, oh my gosh, are you kidding? Most of our tests are like 25. This one, I'm shooting for 50. Most people, like everybody, almost all these tests are done way ahead of time. So after this, after you upload this homework, the next thing coming at you are going to be a bunch of like 20 questions per chapter review things, packets, whatever. I think that I can't remember exactly what it's called. But here's what's going to happen: is I'm not going to try to make this crazy difficult. So for Unit 1, there are going to be 20 questions, and I'm going to pick 4 or 5 questions from that, and I'm not going to copy and paste it straight to the final exam, but the exact type of questions on the review will be on the exam. So, for example, if for the one, like on Chapter 1, if they're talking about like what is a heterogeneous... Juniper! If they're talking about heterogeneous solution, guess what the questions are going to be on? You guarantee it's going to be a question on heterogeneous or homogeneous. Guarantee. Got it? Stuff like that. Really similar questions. Dig into these. I'll give you the answer, and we're going to do some Zooms to answer questions about it. And then your chemistry is going to be done. Good times, everybody. Summers are coming.